Okay. Hi, everybody. Welcome to today's seminar. So today, Natalia Wodka-Cholewa is going to speak about computer-assisted proof of diffusion in an application to PER3BP. So Natalia, take it away.
Thank you very much. I'm Natalia Wodka-Cholewa, and I'm from the University in Krakow, AGH. And thank you for the opportunity to give this talk. I will say something about computer-assisted proofs, diffusion, and something that I do, and maybe some results with my supervisor. So, okay. Oh. Yes. So this everything will be a joint work with my supervisor Maciej Capiński. He's a professor in the AGH University in Krakow, and we did a paper. The paper is about computer-assisted proof in the planar elliptic restricted three-body problem. This is the name, the short name in my title of presentation. And the previous paper that we used the tool from is made by Maciej and Georges and Jean-Philippe and JD. They had some great idea to construct some tools for the computer-assisted proofs. They are like Melnikov sums, but and you can use it instead of if you know what I'm talking about, you know, instead of Melnikov integrals. Okay, so my plan is as follows. I will make some introduction and put some definitions so you know what I'm talking about. I will state the results from the paper, and I will explain some tools that we used in the proof. I won't do the proof because it's a long story and a lot of technical things, but I will show what we use to do computer-assisted proofs. So it's a numerical kind of stuff, and maybe some references if you are interested in further reading. Okay, so we have a planar circular restricted three-body problem. It's restricted because we restrict ourselves to some region, and we only consider some of the trajectories. It's circular because we assume that our bodies are moving on Keplerian orbits that are circular. And three-body problem, we have three bodies. Two of them are bigger, we call them primaries, and it can be Sun and Jupiter. In our case, it can be Earth and Moon and something like this. And the third body we assume is massless, so you don't have the mass. It doesn't have any influence of the larger bodies, and it's only in the influence of these larger bodies, so it moves between them. Okay, and maybe you don't know, we have 5 liberation points in such a system if you consider, for example, Jupiter Sun, and we are interested in the collinear points. So you can say it's Euler points. So we are interested in L1, and you can name them as you want. You can name L1 on the left and L3 on the right. It doesn't really matter if you only say where is it. So we will call L1 as a point between Jupiter and Sun is closer to Jupiter. So you see you have the Sun in the middle, and somewhere is Jupiter going around the Sun, and we consider the we'll be interested in L1, that is between the Jupiter and Sun, close to the Jupiter. And we know that around this point L1, and of course around L2, but we talk about L1, we have Lyapunov orbits. There are orbits around this point that are in the same plane as Jupiter and Sun, because we talk about the planar problem, so we have only two directions, because you know the three-body problem in general is unsolvable, so we have to restrict ourselves to some things to have so we can calculate something, right? So we know that this orbits, we have a family of them, but there are some orbits, and they go in the same plane as the Jupiter and Sun, and they are going around L1. Okay, so we can say something about planar elliptic restricted three-body problem, and then in this problem everything is the same, but we assume that Sun and Jupiter are moving on Keplerian orbits that are elliptic. So we have eccentricity epsilon, and this parameter will be our perturbation. So we will have the circular problem, and we were perturbed by this parameter. So it's like it's small, it's greater than 0, but I wouldn't say what are the interval of this. It's small enough, so we perturb it. So we have the perturbation. Okay. So in our system, the Sun will be close to 0, 0, and we scale the positions of the Sun and Jupiter. So the L1 is closer to the Jupiter. Jupiter is almost -1, because we have the distance between Jupiter and Sun will be 1. So we scale it because of the also because of the mass of the Sun is much greater than the mass of the Jupiter. So you have to scale it, so the everything in calculation is better to do. It's just for the scaling. L1 is still the point right between the Jupiter and Sun, near the Jupiter. Okay. So in our system, I will talk about something about the coordinates and Hamiltonian and how the system works. So we will have positions and momenta of the body. So xy and px and py. So px is the momenta connected with the x direction, and py is the momenta connected with the y direction. Okay, and we have theta, the time in our system. So we have the third body between the two bodies that is moving, and we are interested in this motion. So we have the Hamiltonian for this system. It's rather complicated, but it's really physical. So from the physics, you can take it, and it's just the formula, and it works. So you have the H epsilon. So I'm talking about Hamiltonian for the perturbed system, for the system that is elliptical. So it depends on the position and momenta, and of course on the time. So you have the time in the denominator. You see the cosinus theta with the perturbation. So here's the perturbation. It's somewhere there, and this beautiful long other formula that is connected to the potential energy, right? Because the Hamiltonian express for us energy in this system. Okay, I will not express any of the equations, because you can find them, and we won't do anything with them. So okay. And for epsilon equal 0, we will have a circular problem. So if I say that for epsilon 0, our Hamiltonian will be a Hamiltonian for unperturbed system. So I will say it's H0 of x, and it does not depend on time. You see that if epsilon is 0, there is no time explicitly in the Hamiltonian, so it's autonomous. So it's fine. So we know that there is no time, and we can write x only. Okay, in this system, there is a very interesting symmetry, time reverse symmetry, that this symmetry works as follows. This is the definition of the symmetry. So you can change the sign of the second and the third variable, so y and px, and there is no changing on the first and on the fourth, so x and py. So if you take a point, and you will, so the phi t, it's a flow of our system connected to the Hamiltonian. And if you do the symmetry, that means you get the point that you make a symmetry and go backward in time. So you can use it to, for example, if you choose your points correctly, you can make half of the orbit, and you can, by the symmetry, get the other half, because it's symmetrical reverse in time. So it's really useful if you want to go reverse in time, and it will be really good for us and important. Okay, so this time reverse symmetry works in this Hamiltonian, in this problem. You see in the Hamiltonian, you have some minuses and pluses and some squares, so it works for it. Okay, so I will make now some definitions for you to understand the objects I will talk about. So some manifolds, stable, unstable manifolds, something like this, because it's not so obvious to know what is what, and I will try to explain the intuition, because it's maybe you know this, but the intuition. Okay, so we have a smooth n-dimensional manifold, and we take a compact submanifold without boundary, and it will be invariant. So lambda for me will be an invariant manifold under some diffeomorphism. It's like a smooth CR class diffeomorphism. So I will say that this manifold, invariant manifold, is a normal hyperbolic invariant manifold if there exists some constant c greater than 0 and some constants small lambda and mu that satisfies these inequalities, and there is decomposition to vector bundles for all points from this manifold this way, as you see, and it's TF invariant. So you have the tangent space in point X to our manifold M, and you can decompose it on some parts. So the EU X, ESX, and T X lambda. So it's the last one is connected to the invariant part. The first one is connected to the unstable part. The second in the middle is connected to the stable part. And it's a direct sum of something like this. It's TF invariant. So if you do something and take F in the manifold and do something with the point, it's still on the this tangent vector bundles, you can still do this decomposition. And as you see below, we have some rate conditions, because when you have the vector from this EU, that means backward in time, it's a contraction, because it's k is less than 0, so backward in time, it's a contraction with the rate lambda. And for ES, we have a contraction forward in time, k is greater than 0, and we have rate lambda. And on the other part, that left, we have some motion, but it's you see mu to the -1 is greater than lambda, so it's like a bounding for the movement inside the last part that is invariant. So it's not there is not you don't have a greater expansion, and you don't have greater contraction. It's like you can say it's like a center part. Okay, so we have some hyperbolic, because we have hyperbolicity. It's unstable direction, stable direction, something like this, if you know how it works. And of course, this invariant manifold is like in the center. Okay. So this is the object we will talk about later. Okay, so if we consider we can, for this normally hyperbolic invariant manifold, we can have stable and unstable manifolds, right? So we will consider a small neighborhood of lambda. I see that I forgot the slash here. So it's it's a neighborhood of lambda. It's in M. Of our invariant manifold. And we can define for this neighborhood local stable and unstable manifolds. As you can see, we'll write W, U, or S, depends if it's unstable or stable, and we'll say F because we have to connect it to our diffeomorphism, and U, and of course lambda, big lambda. And for us, for example, this unstable manifold, it's all the points in M that after some iteration backward in time will go to our neighborhood. So backward in time, they go to our neighborhood, and the distance between this application and our manifold is shrinking. So you go backward in time to the lambda, to the manifold. Right, the distance is, it's a manifold. You have some metric, and it's a distance in a normal sense. You can. It depends on the manifold, but it's like the normal metric, right? From the topology. So it's like this is the distance, and y, it's a constant that can depend on y. So sometimes the rate depends on the point that we have. Okay, and of course, similarly, you have the stable manifold, and it's all points that forward in time, they go forward in time. After some iterations, they go to the U, the neighborhood, and the distance is also shrinking. Yeah? So for unstable, we say always backward in time because it's expansion in forward in time, and for stable, it's contraction forward in time. We can also define global stable and unstable manifolds, and it's a union of all the images. And for unstable, it's all images forward, right? And for the stable, backward, because if you have unstable manifold, you have to produce all the points that are going to be later, because they backward in time are in our local manifold. And about the stable one, you have to go backward in time to have all the points that will later be in our neighborhood. So that's why it's a union, and that's why you have the image and the preimage, and it's a union of preimages and all images. And it's hard to about the stable and unstable manifolds, it's hard to prove that they are in fact manifolds. It's not that easy to understand why all the points that go somewhere are all connected and are manifolds. So it's not that easy to understand that, but it's a classic theory, and you can think about it as a intuition that the stable are contraction and unstable are expansion. For our manifolds, local, and of course we can do the same for global. We can do a foliation into fibers. A foliation, you can think about decomposition on small submanifolds that have some properties, more or less. And fibers are this part of the part of our manifold. So you can the foliation goes by the lambda. So you have the unstable manifold WU in point X. So it's not all the lambda, but it's point X, and we see that we have the distance between the image backward in time of our y. It's closer between the image of y and the image of x is shrinking, and similarly for the stable manifold. So all the points that after the iteration will be close to this. So it's a foliation by the lambda. You can think about it like you divide it into some points that are close in backward in time, or forward in time. Okay, so if you do a perturbation, so you have Hamiltonian that depends on time, you can extend your phase space by the time. So you will have one independent variable, it will be theta. So you have one more equation, and you have one more dimension, and it's we always assume that it can be periodic, so that theta can be in one-dimensional torus, so 0 to 1, or you can think about it as an angle, and it's 0 to 2 pi. So it depends how you think about the circle, right? If it's the 0 to 1, or it's an angle on a circle. Okay, so we will denote by phi 0 t a flow for the unperturbed system, and it's in a 4-dimension. We have x, y, px, py, and for the perturbed system we will have one more dimension because we will extend phase space, so it's phi epsilon t, so you have R4 times one-dimensional torus. So t, it's one-dimensional torus, 0, 1. Okay, and we will denote by sigma a Poincare section for our coordinate system. So it's a section for the first return map. Okay, so the standard Poincare section, and it's 3-dimensional, of course, because we work in 4-dimension, and sigma hat will be Poincare section in extended phase space. So we will just take it sigma times one-dimensional torus t. Okay, so this one with the hat will be in extended phase space, and this one without the hat, it's in our coordinate system, it is just 3-dimensional, and it's for unperturbed system, so the circular problem. Okay, we can define a family of Poincare maps on this section for in the extended phase space, and it's a family because it depends on our parameter. So the family depends on the parameter epsilon, and it goes from section to section, of course, and it's associated with the flow for our system. And F0 will be for our unperturbed system, and it of course goes from sigma to sigma without hat. Okay, so we can say that this F epsilon we can divide it into two parts. So it's a Poincare map for the perturbed system. So we have the part from the unperturbed system, so Poincare map from unperturbed, and the perturbation. So some function g that depends on the perturbation and on the point times epsilon. So this is the part that is the perturbation in our Poincare map. And we define it as follows. You have 1 over epsilon, and this is the you have the difference, and for 0 it's a derivative in point 0. As you see, if you put g inside this everything is fine, right? It works. If you put it, it's just the same. So the g is important for us because this measures the difference between the Poincare maps for the unperturbed system and perturbed systems divided by epsilon for our perturbation. So this is something that we want to study and want to know what's going on with it, or maybe some something some calculation do for this g function. So it will be later in the theorem. Okay, so let's forget about some of the things before, and we can consider other coordinates on the section. It doesn't mean that I don't have x, y, and px and py, but I can change it, or I can choose from them. Maybe it's that easy. You can choose which one is which. You will have a different coordinates, and on a section it's 4-dimensional, because the extended phase space it's 5-dimensional. And we can choose, or we can change the coordinates as follows. We will have some coordinate that will be connected to the unstable direction. One will be connected to the stable direction. I will be connected to the energy level. So if you have Hamiltonian, you can always calculate the energy for your point. So this will be for us now coordinate, one of the coordinates, and theta will be, we will say it's an action variable, but it's an angle. It will be on the torus. You can, as I said before, you can say it's it's an interval 1, 0, 0, 1, or you can think about it as an angle from 0 to 2 pi. Okay, so we will assume that we have normally hyperbolic invariant manifold lambda 0, and this is for our unperturbed system. That's why we have the subscript 0. So there exists this invariant manifold there. We can parameterize it in these coordinates on our section, that u and s is 0, and we have this I and theta that parameterize this hyperbolic invariant manifold. So we assume that it exists, and it's like a standard procedure. It exists, and you can parameterize this as this. And after some modification, not really, it's more of a technical thing. You can consider this lambda 0 as a 2-dimensional torus. So the modification includes some narrowing. So I will be now from 0, 1. You can use some bump function and gluing together something that I will show it later how you can glue it. And for us, it will be 2-dimensional torus, because we want to use standard normally hyperbolic invariant theorem that will allow us to say that after the perturbation we have another manifold, it will be lambda epsilon. So this is like a technical thing to do, because we want to have the same invariant manifold after the perturbation. And to do this, you have to consider lambda 0 as without boundary and manifold, and so it will be 2-dimensional torus. I will say about the gluing later, but it's rather technical. So there's another important assumption for the epsilon equals 0. So for the unperturbed system, we assume that energy is preserved. So that means if I say that I is a coordinate that express energy, we have the projection on the coordinate I for f0 over z. It's a projection just with z with. So its energy is preserved, so it doesn't change energy after the movement. So yeah, so it's just like that, right? Because I is our energy level. Okay, so in our setting, because everything before was to prepare us to understand some of the objects and know what are we talking about, and now we have our setting for our Jupiter Sun system and everything that we have in our setting. So we work mostly with the circular problem. That is a good thing, because after the perturbation, who knows what's going on there. So all the calculations are done in the circular problem, so it's good for us. So there's no perturbation. Our Poincare section will be y equals 0. It's on purpose like that. So point L1 lies on this section, right? It was on the x coordinate. So we know that there exists a family of Lyapunov orbits. They are asymmetric, so the time reverse symmetry works because this section is like cutting it in half, and you have the symmetry, everything works. And we will choose a starting point for our Lyapunov orbit as follows. So the x star is fixed, so it's some value, and you have x0, the starting point. You have x star, and some py coordinate. It's some function of, it depends somehow on the x coordinate, right? So it's some function and some value. And you can calculate it. And here we choose this value x star. So this will be the starting point. As you see, y coordinate and px are 0. So we can obtain this symmetry for our orbit. So it's easier to calculate, and it's easier to obtain the orbit. Okay, and let us take this value from this narrow interval. It's narrow, but it's not like nothing. I think in real life in the cosmic space is like 1 kilometer or something. So in our system, so it's not like we take the values from the small interval and it's nothing, but it still make change. So for each value from this interval, we have the corresponding Lyapunov orbit, and it has a different energy. All the orbits has the slightly different energy. And if you take a starting point like this, and you calculate this Lyapunov orbit, you can do it, and it works, and it's our interval here. Okay. So it looks something like this. We have this lambda 0, and u and s are 0, and we have I and theta. So theta, you can think about it as an angle, so it's from 0 to 2 pi, and you have I coordinate, okay? Here it's from r, but it can be narrowed down to 0, 1, and you see that you have energy levels. I is an energy level, so you have these stripes, right? And they go periodically. So these are our Lyapunov orbits. So lambda 0 will be a collection of Lyapunov orbits, and we will take them as I said, taking the starting points with this value x star from the interval. But it looks something like this. It's not x and y coordinate right now in this, but you can think about it as the periodic orbits that have the same energy level. So it looks like stripes right here on this graph. Okay, so I will make another thing that, so if we think about it as a coordinate that express energy, we can take it as a function that for some value we can calculate the energy level. So we take the value. So this function I will be depending on this value, and we put our point in the Hamiltonian, of course, unperturbed system, and we calculate energy level. So for some value that we have x star, we can calculate our energy level like this, taking the starting point, because on the other points on the orbit the energy level is the same, so you can calculate it on the starting point. It doesn't really matter for us. Okay, so we know how to calculate energy. We have our interval, our values, everything is set. Okay, so this is the result. So we're preparing ourselves to understand what is going on here. Okay, this is the main result from the paper. There exists a constant m greater than 0 such that for an arbitrary finite sequence of values from our interval. So we have finite sequence of values, and for sufficiently small perturbation parameter greater than 0, so some small perturbation, there exists a sequence of corresponding times and a point. And as you see, the times and the point depends on the value of the parameter, okay, such that, and we have this inequality holds. And as you see in this inequality, we have I x I star. It's an energy level for the value from this interval, so for some starting point for our Lyapunov orbit, okay. And here we calculate Hamiltonian, so energy level for some point that we go with trajectory for some time in perturbed system. That is really important. It's a perturbed system. So we can say that we epsilon m shadow our orbits, but in a sense of energy. So we shadow the values of our values of energy for our orbits for Lyapunov. So you have the Lyapunov orbit, it has some energy, and you can shadow them by some shadow. You can find the orbits that are near that have the same, almost the same energy level. So if you get the small epsilon, the closer they are. So if the perturbation is smaller, they are closer to each other. So we shadow the energy levels. So we can do that for some finite sequence of values. So yes, we can take it from here, and it's one point that depends on where we are and how the perturbation is, and there are different times, of course, for different values. It's understandable. Okay, so this is the result. Okay, so we can shadow some energy levels of this Lyapunov orbits over point L1. Okay, and it looks something like this. We had like these stripes that are energy levels, so they go by the angle, and they like going around. And if you think about it in the all space, you don't have I, but you have theta here. So x and y, it doesn't really matter if it's a small x, small y, but say it's some coordinates. You see that inside you have like the cylinder, kind of like this one. You have the let's say it's our section, this gray area, it's our section. So you have these stripes here. So these are our Lyapunov orbits inside. They're going around with the this one, and they are for the theta, they are periodic. So it goes like this. So it's not like this tubular thing, but it's more like when you connect it, it's like more like a torus, right? Because it's glued from this from the 0 theta, and from the 2 pi theta is glued. So it's like more like a torus. Okay. Okay. So now I will try to sketch a proof and talk about the tools that we use to obtain everything, how to talk about this, and how to express it. So the main tool will be 5, so existence of diffusing orbits, that we use the tool from the paper I was talking about in the first place. But first, you have to prove some things. You have to prove the existence of this normally hyperbolic invariant manifold, lambda 0. So you have to prove that there are, in fact, this Lyapunov orbits, that there exist. You have to find some bounds on stable and unstable manifolds, so you know where they are. And of course, it's numerical things, so it's like bounds for them, not exactly where they are. You have to prove the existence of the intersection between the stable and unstable manifold. It should be transversal, and some homoclinic channel along. So it will be a curve. If you think about the stable manifold and unstable manifold as some surfaces, you have to find this transversal intersection. And transversal meaning it's not trivial, right? So it goes through. It's not like tangent. It's not tangent. It goes through. Okay, and you have to, as I said before, we want to prove that after the perturbation, our manifold will persist. So persistence, this is the thing I was talking about, it's for. So after the perturbation, it persists. So still you have a normally hyperbolic manifold after the perturbation. And it's all connected to the 5, so existence of these diffusing orbits that are helping us to shadow this energy level. So first, existence of this Lyapunov orbits. We use some tools that are really common for rigorous arithmetic, for people who do some numerics. So we have a parallel shooting. Parallel shooting means that we divided. For example, I want to in our case, I want to prove that I have a periodic orbit. So I do a parallel shooting. I divide this orbit into some parts, equal parts. So we have x1, x2, x3, and everything. And I construct the function f that depends on these points, depends on some m, because I will start from this, and tau is time. So I have some time, and it's a time between these points. Okay, so I take and move by time tau this p of m into near to x1. Okay, and here I make a subtraction, and exactly the same with the x1. I move it near to the x2 and subtract it. And okay, I do it n times, and I have xn. After that, I make one last. I take phi tau, and I will do a projection on our section. It will be our section, and px 0. Why? Because we have the symmetry, right? It's for us to the symmetry. And as you see, I have this function construct. And why I do this? If I found 0 of this function, I will have the connection, because this will be 0, so I'll move to x1. This will be 0. This will be, everything will be 0. And this one and this one, so the projection onto y and projection onto, this should be small y and this should be small p, of course. And I will do a project, and this will be 0. So for me, it's important to find 0 of that function, because all the points will be connected, and I will go from section to section. Okay, and I will say what's PM. We take PM as a starting point, our value x star. So this is the place, and m will be a small parameter that I will have to determine. So this is the thing I'm looking for in my method. So I'm trying to find 0 of that function. So that value m and the time between points and all the points. So this is 0, so everything is connected, and I have a good value m to start with, because I don't know that. I only fix this, and I want to find what should be on the py coordinate, so I have the good starting point, and I will connect everything and go back to the section. Okay, and we do this parallel shooting, and we try to find 0 of that function. And we do this by Newton's method. So it's firstly you do this. It's an algorithm which produces, yes, you have better approximations of 0 of the function, and you can do you can use the Newton's theorem, and it's here. So you take some interval. So we have some function, okay, and it's a smooth C1 function, and you take some cube and dimensional, and by this you take the interval that it's containing this u, so some set u. So if the interval enclosure of we have Jacobi matrix is invertible, so you can invert this. It's a matrix of derivatives, right? So if the matrix of derivatives is invertible, we can use it here, and we can calculate something like this. It's sometimes called Newton's operator or Newton's Krawczyk operator, and you do something like this, and it exists x0, so there exists a new unique point that f has a 0 in this unique point. So it's a theorem that you use to prove that there exists a periodic orbit sometimes, or something. Depends on how you construct your function. We construct our function in parallel shooting, so we have the connection between points, and it will be our from section to section we will go. And if you prove it, so if you take some, say, interval, and you take a point, and you go with this point with the flow, and you go back to the x, it means that inside it's a periodic orbit. You don't put your finger and said, here it is. You have only the estimate when you have to start on what interval you have to start to prove that inside there is Lyapunov orbit, for example, right? So we use this. It's a method in rigorous numerics. So you have to calculate it in the computer. You have to put a set in, you have to put your Hamiltonians, you have to put everything. You have to calculate this n, and try to find out if it's in x, because this is the starting point, starting cube for us. And if it's in, that means it works. And if you put your function correctly, it should be for us the connection. And you can do only a half of the orbit, as I said, because by the symmetry you have the other half. So I go from x0 to x1, and then I can produce by the symmetry the rest of the points. So I have the connection, and it's a full turn. Of course, you can do it without going with the symmetry. You can also, but it's you have there are more points, so the estimate can be worse, right? And you should be really careful with the n, so how many points you choose, because if it's really small interval, it's a really small time between points, you have the matrix of the derivatives, it's not invertible sometimes, or it's like expanding everything. Or if the time is too long, it will also expand, and it will be like the estimate will be not really good for you, because it's like a big interval. So for you, it wasn't big. It wasn't good. Okay. So this is, for example, one of the Lyapunov orbits around L1. You see, L1 is near -1 for us. This is the right now, this is the one of the Lyapunov orbits, because we have the family, and you can calculate from the 0, and then you have -0.995, and you can calculate the half of the orbit, because you go to section again, and then the other half is by symmetry, or you can calculate the whole orbit. It's okay too, and it looks like this. And you can do it also for the L2, and it looks exactly the same but mirrored. So it's very similar with the L2. But we say we will stick to the L1. Okay, so this was our theorem, and we use it very often to, it depends on the function, but it uses it very often to prove that there exists something, some trajectories. Okay, so if you want to find some bounds on stable and unstable manifold, use also Newton's method. So you will be taking some interval and doing something with this and trying to find out if it's inside the previous interval, but use also conditions. Why? Because if you want to have the direction in which goes the stable or unstable manifold, you will have cones. Cones are, as you think, there are some part between they don't have to be like round, they can be like cubic or something, and they look something like this if you think about them and try to they also are named Q plus, because you have like you can go like with the gray area or the white area, it depends on your setting and everything. And the idea is to find the point and v, that it's the unstable vector for the and it's a direction of it's an unstable direction. And if you find for our point 0 lambda, you take the matrix of derivatives and you calculate the unstable ein vector, you know that backward in time, if you go with the function backward, you will be closer and closer to the, of course, it will be origin 0 lambda, but f minus m, right, before. So you are closer and closer. So you are not like outside the cone. So inside, if the cone is narrow, you have the good estimation in the small interval for your manifold. And if you have unstable, you can use the symmetry to produce stable. It's that easy, because it goes reverse in time. So for you it's easy if you have the right setting and you put everything on the section. So y is 0 and of course px is 0. So you have the symmetry, and you can obtain this red curve. It's a stable fiber. It's not a whole it's not whole manifold, but it's one of the fibers, because you take only one point and it's connected to the point, right? So it's WU in this point for this map. So something like this. Okay. Okay, and it looks something like this. You know, we have a family of orbits, so you can calculate one fiber for the one orbit. So let's say we had one orbit, and we calculated the unstable manifold, and we were like turning around the L1. We go to the left, and here when you have 0 and after the near the -105, you have the you have the section, and this will be the connection to the stable manifold. So it's not unstable, it's stable and unstable, because the reverse in time looks symmetrical. So they are connected in the point that is far on the left for this trajectory. Okay? So I can calculate, firstly, it goes around the L1, goes farther and farther, and goes to the left to the our section. And by the symmetry, I have everything backward in time. So the stable goes there, and it's going on the near the L1, and it's going to be closer and closer to the Lyapunov orbit. Okay, for the existence of this intersection, when we have stable and unstable manifolds, we do something similar. So we have to start in some point on our on our orbit, Lyapunov orbit, but we have to move in the direction of the unstable manifold. So PU, it's a this unstable fiber. So you put yourself somewhere near this 0, 0, x star 0, 0, m, and you move in the unstable direction. So you can take this cone and move on the unstable manifold to the section, and you do this the same for the stable. So you have two cones that are on the intersection, and that's the idea how to say it's transversal, because cones are, if it's narrow enough, you have the direction and you have the dimensions, okay, because it will be a vector. We will consider of course, the energy level will be fixed, and we'll consider a three-dimensional space. So you have to prove that if it's transversal intersection, you have to find 3 dimensions. Okay, so yeah, the tangent space has to be 3-dimensional, so it's a transversal intersection. So you put these cones, and you go with one cone from the stable, one cone from unstable manifold, and you have to show that this vectors in the cones are not going onto each other. So you have the directions separately, right? Okay, and we have to check some conditions, and if the common channel is well defined, but it's just checking the tangent spaces if there are they have all the directions we need, or the dimensions. I won't put it in here because it's rather technical, and it's a lot of a lot of work to write everything and understand why it is. It's pretty easy, but you have to write everything down to see if you have this direction, you have this direction, and it's everything is as you like. And this common channel, you can parameterize it by the you have the theta, of course, it's an angle, but you have this curve that it's an intersection. This small gamma of I, it's an intersection. It's a one-dimensional curve, and this is our common channel. So we go along the intersection, and we change only the angle. So this will be our channel. It's some sort of, if you think about it, some sort of neighborhood of the intersection. Okay, so if you want to prove the persistence of the normal hyperbolic invariant manifold, you want to do some modification to a vector field. So you can use the standard normal hyperbolic invariant theorem. And to do that, you have to treat this lambda 0, as I said, as a 2-dimensional torus. So you do some gluing. You use some bump function. So this is the idea. You have the Hamiltonian. You modify it by the bump function b. So you have in some area, you can see here, you have the on the left picture, you have the elliptic problem between A prime prime and B prime prime, and you have glued to the circular problem, and between you have the small interval that you do some smooth connection, right? If you know how the bump function works, you think about this as a something like this. So you have the you can do it as an exponenta with minus x square or something like this. It doesn't really matter. It's a smooth connection between the elliptic problem and the circular problem. So at the end of A and B, you have the circular problem. In between, you go smoothly to the elliptic problem. That's how you modify the Hamiltonian. And inside, you have the elliptic problem. And then you glue it like on the right side. So you glue it with the B, and you have A on the bottom and on the top, and you glue it again, so you have the torus. It sounds crazy because you have all these dimensions and you don't know where they are, but it's a complicated idea, but it gives you the smooth connection between the circular and the elliptic one, and then after this modification to the Hamiltonian, you can treat this lambda 0 as a torus because it will look like this. If you want to know something more about it, here's a paper that has every detail about this gluing, how to do it, and why this works. Because the first thing is, there's a lemma for that. The first thing is that you glue and you modify this Hamiltonian and you do some torus, and it's complicated. But then you have to prove that some properties are working, right? That you can treat it as a normal version, but let's say you now narrow this I to the 0, 1, and it's not R, right? So why it's work? You can check it if you want, and the theorem says that we have only to check some derivatives that with respect to this our value that are non-zero, and then it works. So if we check, for us it's only checking these derivatives, but under this there's a lot of work for the modification. We didn't do the modification. It's like inside this theorem that works, and if you check it, it's rather simple to, you only calculate it with your computer, and you check it's not 0, so it's fine, and you can use the standard theorem, and you know after the perturbation this persists and everything is okay. But the modification is rather complicated and technical, and you have to do something about you have to check that derivatives works and everything is okay on the manifold. Okay, so the last part of the proof is the main tool. It's the most, because the previous ones are like very common tools to use, and this is the tool that came from this paper. As you see, this paper was submitted in 2021, but it was published in March in 2022. And it has the tool to prove this existence of diffusing orbit, and I will talk about it. It will look like a lot of formulas, but it's not that bad. Let's define a strip. So we consider a topology on our invariant manifold for, of course, our I from 0 to 1. Okay, so we say that this S open set inside is a strip if you cut it with this any point, it's non-zero for any k. So it looks like this. Maybe this will be for us. The other coordinates are here and I is here. So you fulfill every value of I. Okay, so this strip looks like this. So you have something like this. And the picture says probably more than the definition. We want to have every value of I from 0 to 1. Okay, so the theorem, I will say, will allow us to find the orbits that change the energy level. So I will increase in the perturbed system, but everything we will check on the unperturbed system. So this is the theorem. We have some neighborhood of our invariant manifold on unperturbed system, some constant bigger than 0 Lg. We take, and for every point from our manifold, and this point is from, as you see, the unstable manifold of Z, and this is the stable, of course, local manifold of Z. And for this point, we have something like this. It's Lipschitz like um, mm, it's Lipschitz like inequalities, right? So you have on the I coordinate, you take the um, um, difference between G0 xu and G0 z. So it's this G is as previous, and it's in unperturbed systems because epsilon is 0. And you see, this is the difference between the Poincare map um, in this point, but for the coordinate I. Okay, it's bounded and for stable as well. Okay, so you also assume that for some constant c and some constant small lambda from 0, 1, such that you have also the point from the manifold and 2 points as previous from the stable part and unstable part, this holds. So you see that it's then you take the images of z and xu, and it's bounded forward in time and backward in time. This is the hyperbolicity. So yes, this is the looks like great conditions because this is the hyperbolicity. So you have the expansion and you have contraction, right? So z is it's going close here for backward in time, and here we have forward in time. So we assume also we have some sequence of some scattering maps, some maps that are defined on our manifold, and assume that after the here exists the constants and everything, but we take the this map over Z, we iterate it, and it will finally goes to our strip. Okay, so after some iteration, we take some point and we will go to the strip forward. And also the main thing to check, we have some, there will be a picture, it will be easier to understand. We have some point here, X, it's in the intersection of the unstable and unstable manifold, but for unstable it's Z, and for stable it's this point after the moving it somewhere. And this is the iteration for our point X, and we'll go to the stable manifold, of course, for this point. And this inequality, we have to assume that it works. So you have the sum and some other things, and it's bigger than 0. So this sum represents, it's like Mielnikov sum. So it represents Mielnikov integral, and these are the things that it's hard to calculate. When you calculate Mielnikov integral, you have a hard time to bound the you calculate main value, and you have to calculate everything, and this is helping you to approximate this thing that has left to calculate, and this is the main value. So this represents, and you see that you sum the energies for G for every point that you go from X to Fm0 of X. So maybe a picture, of course, and then because this is all the assumptions, and then for some sufficiently small epsilon, so for sufficiently small perturbation, there exists a point and the number of iterates such that I see that it's okay. Okay, so I have to jump here because I see my slide was cut off, and it's here. So you have the number of iterates here, and you calculate it on the z0 epsilon, and it's a projection to the I coordinate. And if you take some sequence of given values of the energy, it's epsilon m shadow. So here after this you have the same formula, but I think I did something wrong and it cut it off. But roughly speaking, for sufficiently small epsilon, we have a point that after some iterates, it will change the energy. So you will have the change on the energy. So you can, if you can change, it will be this diffusing orbits. So you can do a corresponding theorem for the I that decreases, and you can combine it into this theorem that is a combining of these two things, that you have the strip plus and strip minus, and you have this shadowing. So there exists m, a constant, and for the given sequence of the I, this will be our values of energy. So we have the sequence of values energy. For sufficiently small epsilon greater than 0, there exists an orbit of this f epsilon, so for our perturbed system, which epsilon m shadows this action, so this energy levels. So there exists a point and a sequence of integers, so this will be iterates, such that, as you see, after some the point z will be iterate into the place that the energy level is the same as in the given sequence. So you can shadow the energy levels. So use that for our the fifth point. So to show that we can do this. Our is similar, and we use it to find it and calculate it. So you calculate. The important thing is to check all the conditions here. So you check this one, and you check the hyperbolicity, and you have to check this sum. So you calculate the sum here in 6, and every constant that is here you calculate, and you try to find if it's bigger than 0. So that's the main tool and main thing from this really rather technical theorem that is has a lot of assumptions, but this is the main thing that it's better to calculate than the integrals, because it's a sum. So you put your setting and try to find if this hyperbolicity and everything works, and you take points from where you have to, and you have this because you have the bounds for the manifolds, and you calculate the sum with this rest, and you have to check if it's bigger than 0. Okay, and it works. So you have the energy level. This is the picture for the theorem. So you have this x that is close to z, and it's on the intersection of the manifolds, and it goes, this black dots goes to the right, and you see that on lambda 0 you also go to the right, and this scattering map will be just a shift map, so it will just move on the lambda 0, because you have lambda 0 and you go only with time. So you will move with time on the right, and you have to go, and what you measure is the difference between these points. So you have this x that goes around above, and you in the sum you check the values of g, so you check the difference between them. So this one is here and this one is here, okay, because you get x and z. Okay, so x has to be close to the z, because we start close to, and this scattering map, as I said, this map, the sigma, it's just a shift map, so it's a time shift map, so you just move with the time on the lambda 0, and you get to be close to the here on the right side, you go to close here. So it's like the you calculate the differences between these black points above and on the lambda 0. Okay, so we perform every step with our with our computer-assisted proof with the assistance of as I said before, we use the Newton's theorem, conditions and everything, and perform on the computer. So you put everything, you do it in a C++, and you have to use some tools because it's not that obvious. Some solvers for the system, for everything, and our main tool was the library CIPD. It's done by people on Jagiellonian University. There's a site, you can take it for free. You can just download it and use it. There are some, for example, this article explains a lot of things, how to do rigorous numerical analysis for dynamical systems. So you can read something like this and be able to calculate some things in some systems. Of course, you have to know how it works, how to define your maps into it and your motion and everything, your whole system. But it's really it's well written, and you can talk to some people that are doing this. Some PhD students do this and support it, so it's growing a lot. So you can do many more things than I do from it, because they are always expanding it. And I think Daniel Wilczak is he is the main person that is taking care of this library, and it's used not only for this three-body problem. You can use it for central configuration. You can use it for some application to the also, I think, discrete dynamical systems, but mostly for the you use the solvers, and you can have the Poincare section, and the Poincare maps, for example, it's calculating itself. So it's really good for you to put your equations in, and it's just calculating for you if you know how to ask for them. Okay, so some references. The first one is our paper. The second one has the tool that we use for the diffusing orbits. That was rather complicated, but it turns out it's only to calculate the sum and try to find if it's bigger than 0. And some other about Arnold diffusion, that you have the in some of it, you have the proof for the diffusion analytically, not with the aid of the computer, and some other stuff that you can find. The first one is you can find some how to do econ conditions and how to calculate it in rigorous mathematics. The second one has the idea to write our paper. So there was it's a near L2, but there are some things that are similar to L1. And the third one, you have some technical lemmas that you can use for our paper. So I think that's all. Thank you for attention. And if you have some questions, you can ask or write to me an email if you want.
Okay, so are there any questions? Okay, so if not, let's all thank Natalia. It was a very interesting talk. We're very happy to have you.
Yeah, it was really great to have a talk. And if someone had some questions later, if you watch it and want to ask me something, you can write me an email and I will try to answer.
Okay, great. Just a reminder, in this forum, if it interests anyone, tomorrow there's the Abel Prize talk of the Technion. It will be available in the same Zoom link on 12:30 Israel time, about the mathematics of Luis Caffarelli. So if everyone is interested.
Yeah, I've heard that there will be Abel Prize talk, yes.
Great. So I guess see you all next week, I think.
Yeah.
So
See
see
you.
ya.
Thank you very much. Bye.
Welcome.
Thank you.
Bye bye.
Goodbye.